Thank you all so much for joining us today for Seeing Through Epidemiologic Fallacies, How Statistics Safeguard Scientific Communication in a Polarized Era. Today's session is being recorded and will be posted for AAAS members after the event. Closed captioning is available. You can enable it by using the CC button on your Zoom screen. Please use the Q&A tab to submit questions for our speaker at any time in the presentation. The chat feature is visible only to panelists and staff, so if you have any technical issues, you can reach us that way. This discussion is intended to provide ideas and foster dialogue. Speakers do not represent the positions and opinions of AAAS. My name is Tori Espensen, and I am the training director for a program here at AAAS called SciLine, which works with scientists and journalists to bring scientific evidence to general audiences through news stories. We've been doing a lot of work around vaccines lately for the same reasons that I'm guessing many of you are here right now. For many reasons, epidemiology, vaccines, and public health have been in the news a lot lately. That's why I'm happy to welcome you to today's session, which is co-hosted by two AAAS sections. Section U, which represents statistics, and Section Y, which represents general interest in science and engineering. For those who may be new to AAAS, the sections are disciplinary communities within the association, 24 in total, spanning every field of science, engineering, and education, from mathematics and chemistry to social sciences, communication, and public engagement. Each section connects members who share an interest in that given area and is open to anyone. Scientists, educators, students, or members of the public who want to engage with science and its impact on society. Today's collaboration between sections U and Y reflects that spirit of interdisciplinary engagement, combining rigorous statistical thinking with a broad public-facing perspective on how we communicate evidence and build trust in science. And now I would love to introduce our moderator and intrepid captain for today's conversation, Dr. Bill Hallman. Dr. Hallman is a distinguished professor in the Department of Human Ecology at Rutgers University. An experimental psychologist, Bill's research focuses on perception of risk and science and risk communication associated with food, health, technology, and the environment. He's a fellow of AAAS, Section Y, in fact, a fellow of the Society for Risk Analysis, and a distinguished research fellow at the Annenberg Public Policy Center at the University of Pennsylvania. He served as the chair of the FDA's Risk Communication Advisory Committee and as a member of numerous committees of the National Academies, including the Standing Committee on Advancing Science Communication, the Climate Communications Initiative, and the Climate Crossroads Advisory Committee. So thank you so much for joining us today, Dr. Hallman, and now that captain's chair is all yours.
Thanks so much. And it's my pleasure to introduce our speaker today. Dr. Jeffrey Morris is the George S. Pepper Professor of Public Health and Preventive Medicine and Professor and Chief of the Division of Biostatistics at the Perelman School of Medicine at the University of Pennsylvania. He obtained his PhD in 2000 in statistics from Texas A&M University and spent 19 years in the Department of Biostatistics at the University of Texas MD Anderson Cancer Center before moving to the University of Pennsylvania in 2019. His primary research involves the development of flexible statistical and machine learning tools to extract knowledge from complex data from emerging technologies, including wearable devices, imaging, and multi-platform genomics. He also engages in interdisciplinary research in various areas of medicine, with a particular focus on oncology, including the development of a device to classify colorectal tumors into molecular subtypes and devising a new blood biomarker index for liver cancer. Dr. Morris is a fellow of the American Statistical Association and the Institute for Mathematical Statistics, and he served in numerous professional leadership roles in the statistical community. Since the COVID-19 pandemic, he's become heavily involved in scientific communication with the media and social media, and has recently started collaborating with the Annenberg Public Policy Center at the University of Pennsylvania. So welcome, Jeff. I'll turn it over to you.
All right, thank you, Bill, and I want to thank AAAS for inviting me to give this webinar, and thank you to everybody who is attending. Okay, let me make sure everything is sharing okay. So let's see. Okay, so let me know if my screen's not sharing okay. Okay, so today I'm going to talk some about my experiences during the pandemic and since involving scientific communication and especially statistical and epidemiological fallacies and the role of scientists in engaging with the public on these issues. Okay, so to start, our medical system is based on evidence-based medicine, which requires effective learning from the data. And randomized trials enable unbiased estimation of treatment effects, so we're the gold standard, but it's not possible to conduct randomized controlled trials for every clinical question, and real-world observational data are increasingly available. So we need to learn from them as well to figure out how to best treat our patients. And observational data are extremely tricky to interpret properly, especially because of the non-random assignment to treatment. Confounders, selection bias, and other issues make it difficult to interpret the data. And even really smart, well-meaning people can misinterpret observational data. It's also possible for smart people with hidden or explicit agendas to distort observational data results to promote their narratives, and often do. So the pandemic and post-pandemic period has raised interest in the general public towards biomedical research and public health and has highlighted these issues. Okay, and so in polarized times, including during the pandemic and even now, agenda-driven voices often misread or misrepresent data that can weaken public health advice and erode public trust. So this can prevent policymakers from seeing clearly to formulate effective recommendations, but it can also undermine the public's response to effective public health advice. So in this webinar, I'm going to describe some case studies where seemingly plain readings of observational data were wrong or scientifically unsupported upon closer analysis. And many of these are textbook examples of common epidemiological fallacies and principles. So the goal for what I'm going to talk about today is to clarify some common pitfalls in interpreting observational data, especially those that are commonly exploited to mislead people. I also share some examples of my work evaluating emerging evidence and trying to counter misinformation or disinformation or unsupported conclusions from key papers. And also, I would like to encourage more scientists to engage with the media and the public. And in the process, I'll convey practical values and strategies that I have for effective engagement and for scientific communication. Okay, so first of all, how did I get involved in scientific communication? I'd never done any of this before in the first 20 years of my career, but when the pandemic came, there was this novel virus that disrupted us. I saw all kinds of claims circulating on social media, and it wasn't clear what was true. So I tried to just use my skills as a statistical scientist in biomedical research to evaluate the information and tried to pass on good information at first via Facebook to my friends. And my Facebook friends run the whole gamut of the most educated people that I know to people without much education, from the most liberal to the most conservative and everything in between. And then later I started a website and blog, covid-datascience.com, to provide a more permanent and broadly impactful revenue. Then at the end of 2021, I transitioned more to Twitter, and there's my handle on Twitter for this work. And so my goal was to use my perspective as a statistical data scientist to critically evaluate emerging COVID-19 information, filtering out biases, aggregating information across studies, uncovering key insights, and trying to communicate them the best I could in an accessible, balanced way while conveying uncertainty. So in that process, it resulted in me debunking misinformation from government and skeptics alike, and also being used by media and fact-checking organizations as part of scientific communication efforts. And now I continue to work with the media, especially when important studies seem to be misread or misrepresented. Okay, so what I'm going to start is present a couple case studies that illustrate some key principles that people get wrong, and to illustrate some of the work that I've done in this area and how sometimes some seemingly obvious results are not as they appear when you critically evaluate them using principles of science. Okay, so first of all, how can vaccines be working if most hospitalized were vaccinated? So in the summer of 2021, after vaccines had been out maybe 6 months, there were reports of waning immune protection out of Israel, one of the first vaccinated places, as Delta surged in various locations, producing breakthrough infections. Various media and social media reports started noting how many infections and hospitalizations were in the fully vaccinated, creating a narrative that vaccines were not working. So here's one report that 60% of the hospitalized COVID patients in Israel were fully vaccinated. So how could this be true if the vaccines were really working? Well, the Israeli Ministry of Health posted data in August 2021 with all active severe infections split by vaccination status. And indeed, out of all of them, 60% were in the fully vaccinated. So on first glance, I can see where people would think vaccines don't work. But if we look a little closer, at that time, nearly 80% of the adults were fully vaccinated. So here are the vaccination numbers and the unvaccinated. So once we use those as the denominators and we compute the rate of severe cases at that time, then you see that it tells a little bit different story. And then if you compute the relative rate difference between the vaccinated and the unvaccinated, you see that the vaccinated were about 2/3 less likely to have severe COVID than the unvaccinated. So that suggested that there was some effectiveness. So why the 60%? Well, because most were vaccinated. And that's an example of something called the base rate fallacy. When an intervention has a high base rate in the population, then a large number of events can occur in those with the intervention, even if the intervention has high effectiveness. You need to divide by the denominator simply. Okay, so, but still 67.5% doesn't look very good compared to what we were told and what the study supposedly showed. However, Israel also posted the data split out by under 50 years old and older than 50 years old. And if you look at that, notice that over 90% of the over 50-year-olds were vaccinated. And if you look at the unvaccinated, over 80% of them were under 50 years old. Well, of course, old people have a higher risk of death. So, and you can see that if you look in the unvaccinated, or I'm sorry, not just death, but also severe cases. So when you look at the severe cases, these were the rates of severe cases in the younger and the older. And you can see that the older had more than 20 times higher risk of severe disease than the younger. Then if we look in the vaccinated, we see a similar ratio. So then once we have these rates, we can compute the relative risk reduction separately in the young and the old, and we get 92% and 85%. So that's a little unusual. How can it be that if you look at it separately, you get around 85, 92%, but when you put them together, you get 67.5%? That seems counterintuitive. So why is that? Well, it's an example of something called Simpson's paradox. Okay, and this has come up a lot during the pandemic. So I pointed this out in a blog post, and this was my first one that really went viral, had almost 1 million downloads. And this was cited in major newspapers in Italy and in Spain and in Germany after I posted it, because this was a question of contemporary importance. And this has sort of become a textbook example of Simpson's paradox that some people have used. So to explain Simpson's paradox real quick, this is a situation where the association between two variables is qualitatively different than if you control for a third variable z. So here, suppose we have a dose of a drug X and a clinical outcome where high is good, and these are the results. If you look at this, it looks like the higher the dose, the better the outcome, suggesting the drug is good. But these 2 point clouds suppose that these are the older people and these are the younger people. So when you estimate the association separately, you see that both of them are strictly downhill, showing that the higher the dose, the worse the clinical outcome. So this drug would actually be disastrous for everybody. But if you ignore the confounder age, you would draw the wrong association. It would go in the opposite direction. So this is what Simpson's paradox, that's Simpson's paradox, where if you ignore a confounding factor, that is a factor that causally impacts both the intervention, in our case, vaccination, and the outcome, severe disease, if you ignore that factor, you can get completely wrong associations. Okay, and there's another example where this came up in the pandemic. And this has to do with deaths after vaccination. So in November 2021, the Office of National Statistics released weekly all-cause mortality data split by vaccination status, and they reported results by age groups, 80 plus, 70s, 60s, and 10 to 59 years. Well, social media posts based on these data claimed that vaccines must have been killing people. One example is blog posts from a very popular influencer, Alex Berenson. So he wrote this post and plotted the data, where indeed the brown line is weekly deaths from vaccinated people in the 10 to 59 age group. The blue line is weekly deaths from unvaccinated people, and the vaccinated had double the risk of death. So his conclusion was, I don't know how to explain this other than vaccine-caused mortality. So this type of argument has helped fuel claims that vaccines killed more than they saved. But what else could explain this other than vaccinated? Well, we also had information from the UK about vaccination rates by 5-year age groups. So from that, at this time period, we can break down the vaccinated population 10 to 59-year age group to find what percent were in each 5-year age group. And then for the unvaccinated, what percent were in each 5-year age group. So you can see that the age distribution was vastly different, with the unvaccinated much younger and the vaccinated much older. Because we can find actuarial table data on the expected mortality rate per 100,000 for each of these 5-year age groups, you can see that the upper end is over 50 times higher death rate than the lower end. So from this, we could look at the age distribution and we could compute what we would expect the death rate to be in the vaccinated and the unvaccinated population. And when you look at that, you would expect it to be 2.4 times greater in the vaccinated simply because they were older. And what was seen was 2 times greater. So it was actually even suggesting potential protective effects. So again, this is another example of age confounding and another example of Simpson's paradox going on. So it was interesting because I did a blog post on this and it got a little bit of attention, but then one day I just decided to kind of get cute and I changed the context and I said, instead of vaccinated, these were people that watched the older Ghostbusters movie. These were people that watched the younger Ghostbusters movie. And I did a tongue-in-cheek post and a Twitter thread saying, oh my goodness, they need to remove the older Ghostbusters movie, from circulation because it's killing people. I can't think of any explanation other than that movie is killing people because the people that watch that movie are dying at double the rate and walking through the exact same age distribution, pretending it's that context. And then at the end saying, oh, maybe it's age confounding, not not the Ghostbusters movie, and maybe someone should tell Alex Berenson that. And so once I sort of told it in a snarky way, it got a lot more attention and ended up going viral on Twitter. So unfortunately, it shows how sometimes being snarky gets more attention than giving the straight scientific information. Okay, so another example I'm going to mention involves what's called the post hoc ergo propter hoc fallacy, which means basically because it preceded, it must have caused. And one thing we saw at various times in the pandemic, but in particular in late 2021, was claims that how could the vaccines have worked if Singapore's infection rate went up as soon as they vaccinated people? Maybe the vaccines are actually making things worse. So this is an example of time confounding, comparing outcomes before and after vaccination rolls out are not sufficient to estimate vaccine effects because there could be many other factors that change during that time period as well. So if we look at the case of Singapore, on the surface, I can see why people said that. So here is the percent vaccinated in Singapore over time. They started in early 2021, and they had over 80% fully vaccinated by September. And then if you look at their infections and deaths, right when they completed the vaccination, all of a sudden they had a massive Delta spike and then a massive Omicron spike, bigger than anything before vaccination. So you could see why people might think that. So does this mean that vaccines made things worse, or were there other factors involved? Well, Singapore had one of the strictest zero COVID policies in the world, and they kept it in place for almost 18 months. And they didn't lift these strict mitigation until August 2021 when everyone got vaccinated. So this enabled the COVID to spread and people to experience exposure for the first time. And the strict lockdown kept everyone from not being infected before. So nobody was previously infected. So all the unvaccinated were completely unprotected. So this kind of shows what could be going on here, that there's an apparent association between vaccine rollout completing and the COVID case and death rate. But because it was a place with zero COVID mitigation policies, they then relaxed the zero COVID policies once the vaccine rollout was complete. So this allowed people to mix together, allowed people to travel, which allowed the virus that was there to spread and people to be exposed. And then on top of that, no one unvaccinated was previously infected, so they were especially vulnerable. So this could be driving the effect. So it's possible the vaccine had an effect, a positive effect, reducing the risk, and you still see this. And in fact, that's what the data suggests. So here is the severe and fatal COVID-19 incidence by vaccination status. It was much, much lower in the vaccinated right at the same period of time. So the claims that vaccination somehow worsened Singapore's pandemic are unfounded. And the increase in 2021 and 2022 relative to 2020 does not imply vaccines don't work. So really the relevant comparison isn't before to after vaccination, because many other factors changed. Really the vaccine effect, you have to think about the counterfactual of comparing what happened during the Delta and Omicron surges under the conditions of vaccination to what would have happened if they hadn't vaccinated their population. But we never get to see that counterfactual. So it's very difficult to estimate that. But interestingly, we have another part of the world that had a similar phenomenon that might give us a glimpse of what that counterfactual would have looked like. And that's Hong Kong. Hong Kong also had strict zero COVID policies in place that kept their infections low through fall 2021. And then they had major surges. So this surge is in early 2022. That was an Omicron surge. Now, the difference, though, is unlike Singapore that had a relatively low death rate, Hong Kong had an astronomically high COVID death rate at that time, which in fact was the highest COVID death rate of any time or place in the pandemic. And this was supposedly less severe Omicron. So what was going on in Hong Kong that was so different? Well, the blue is the vaccination rates in Singapore. They were highly vaccinated in all age groups. Hong Kong, for some reason, had very, very low vaccination rates in their older population. Less than 20% were fully vaccinated at 80 plus years when this Omicron wave hit. And what happened? This is what happened. So it's possible that the difference is the vaccination, that more of the unvaccinated were vulnerable. And indeed, there was data published by an epidemiologist in Hong Kong that suggested there was a much, much lower risk of severe or fatal disease in the vaccinated than in the unvaccinated across all age groups. And there were data that were released that showed case fatality rates by age in Singapore and Hong Kong. They were very similar, much lower in the vaccinated. So the key difference between Singapore and Hong Kong appeared to be the fact that Singapore was all vaccinated and Hong Kong, the older especially, were largely not. So Hong Kong gives us a glimpse of what might have appeared, what might have happened all over the world when Delta and Omicron hit if there had been no vaccines. But we don't get to see that. So I have an American Journal of Epidemiology commentary article that talks about some of these cases and talks some about the vaccine effectiveness data, and also replies to a letter to the editor raising some other issues about negative effectiveness that you can look at. But now I'm going to transition over to talk about some post-pandemic examples. Okay, so one here. So as we know, as RFK was put in as HHS secretary, there's been a lot of changes in the government, and one thing he did was he hired David Gare, a man with a bachelor's in biology, to play a key role in gathering information from CDC data about the potential role of vaccines in autism. And the Vaccine Safety Data Link is a CDC database consisting of medical record data that's used to monitor vaccine safety. So Gare and his father accessed this in the early 2000s for some papers. His access was suspended for violating research protocols by trying to remove the files. But then he and his father published many papers suggesting vaccine harm, including 9 vaccine safety data link papers between 2015 and 2018, claiming to show associations between hepatitis B vaccines and various outcomes, including autism. And these papers were heavily cited in RFK's 2014 thimerosal book, since this vaccine had thimerosal. And RFK's new ACIP committee is likely to end recommendation for universal infant hepatitis B vaccines. So this question is relevant. Well, when David Gare was named back in April in this role, I had some concerns about it, but I wanted to go and see his prior work to see whether it was solid scientifically or not. So what is the scientific quality of these papers? So I found this paper, Gare, Kern, and Gare, that was assessing the potential association of Hep B exposure and atypical autism diagnosis. So this data was using vaccine safety data link data starting in 2020 or 1991, and did a case control study where they found cases where individuals born between 91 and 98 with autism. The controls were over 15,000 born in 91 and 92, not diagnosed with autism. And so they looked at the association between these, and they saw that 55% of the vaccinated had autism, were diagnosed with autism, or 55% of them were diagnosed with autism. Diagnosed with autism had the vaccine, while only 20% of the controls did, which resulted in an odds ratio of 5.0 that they interpreted as a 5-fold increased risk, which is an incredibly strong association suggesting autism links. However, notice that they use 91 to 98 for the cases and 91 to 92 for the controls. Could this induce some bias? Well, if we look at hepatitis B vaccination that they were studying, the coverage just started in 1991. That was when they first started the universal hepatitis B vaccine recommendation. And in 91 and 92, very few, less than 10% were vaccinated. But very quickly, it moved up to, by 1998, greater than 90% were vaccinated. So can this induce a bias? Can the differential time periods induce bias in this setting? Well, to investigate this, I looked at another setting. So I looked at cell phone use in Sri Lanka that increased from 10 to 80% from 2001 to 2009, and then looked at potential association with the likelihood of a woman giving a live birth to see if cell phone use affects the ability to have a baby. So we have this data. So it's sort of a similar setup to the Gare study. Now, the cell phone usage percentage and the live births and the female population numbers in Sri Lanka are real data, but we can't really test this because we don't have the live births split by this woman's cell phone usage. But what I did was what we call a null simulation, where I simulated the splits under the assumption that there is absolutely no association, that the percentage with cell phones is exactly the same in those with and without live births, and then assessed a case control study similar to what Gare did. So the first thing I did was simulate a case control study using all the data for all the years. And once I do that, we see that in the cell phone group, 3.6% had live births. In the no cell phone group, 3.6% had live births. So the odds ratio was 0.98, which is essentially 1, and it correctly found there's no difference, which we know because we constructed it that way. Well, what if we did our study the way Gare did? So we'll do for the cases, we're going to take all the years with the high cell phone usage, but we're only going to pick the first 4 years for the controls, for the ones that did not have a baby. So once we do that, notice that Those with the cell phone, 26% had live births. Those without a cell phone, 6% had live births. So we get an odds ratio of 5.34. So we would conclude that cell phone use increases your fertility or likelihood of having a baby by over 5-fold. That's a completely spurious result induced by this design. And that's exactly what he did in the autism study. So was it just that study? No, he published 9 studies between 2015 and 2018 with the same vaccine safety data link data that he accessed but was taken away from him in 2004, but he still used it to publish all these papers. Every one of these papers showed all of these chronic diseases that were purportedly then caused by Hep B vaccines with large odds ratios. All of them did the same thing. They used the whole time period for cases and a shortened time period for the controls. Crazy. Okay, so I'm going to end with one more example. And this one is not so crazy. This is a study that just came out in the last couple of weeks that looks like a good study, but it shows how difficult it is to interpret observational data. So one discussion from COVID-19 vaccines online is that they cause turbo cancer, that there's all these cancers coming from use of the vaccine. So here's this new study that came from national Korean data from 2021 to 2023, looking at whether cancer diagnoses are greater in the year after COVID vaccination than in an unvaccinated control. So they compared, based on primary vaccination in 2021, 2.4 million that received the COVID primary vaccine versus about 600,000 who did not get vaccinated. And then they use something called propensity score matching between the groups to adjust for any confounding or systematic differences in age, sex, socioeconomic status, comorbidities, and infection history, which is a good thing to do. They also did a second analysis in 2022, 2023, when boosters were going around, and they compared 700,000 boosted to 350,000 non-boosted, again, matched. And they compared the cumulative incidences of cancer diagnoses. And since they have centralized medical records, they have reliable measurements of this in the vaccinated and the unvaccinated using multivariate Cox models. They stratified their outcomes by age, sex, and vaccine type, splitting by mRNA vaccines or the DNA vaccines. And they also presented comparative results of the differences at 1 month after vaccination, 3 month, 6 month, 9 month, and 12 month. So, and the study both looked at overall cancer diagnoses and the incidence of many individual cancer types. So what were their results? Well, this shows their results as the hazard ratio, the hazard ratio between vaccinated and unvaccinated. So 1 means there's no difference. Anything above 1 means the vaccinated had a higher incidence of cancer. And these are the confidence intervals. So anywhere the confidence intervals are completely above 1 shows it's a significant effect. So they found that for primary vaccination, they found a statistically significant effect that suggested a 27% increase in cancer diagnoses within 1 year of vaccination. And when you look at individual cancers, some of them didn't have an effect, but the ones that had a significant effect were thyroid, gastric, colorectal, lung, breast, and prostate. So on the surface, this looks like a very strong study showing that maybe vaccines, COVID vaccines, are causing an increase in cancer, which is what some people have been saying. And it's been portrayed that way. An interesting thing is when you split it by vaccine type, the effect is especially strong in the non-mRNA vaccines, but there also was still an effect in the mRNA vaccines. But then interestingly, when you look at the boosters, the hazard ratio was 1.01. So there was no evidence of any increased risk of cancer after a booster, but there is after the primary vaccination. And when you look at the individual cancers, you flag gastric and pancreatic cancer, and then you actually see that leukemia had a statistically significant lower effect, where those that received booster vaccines had a lower risk of leukemia. So on the surface, the data in the study appears strong, but if we look more closely at it, it might not be quite as strong as it looks. So is the result we see biology, or is there some bias? Well, they I mentioned they presented the results split out by months. So here are the hazard. So look at the black for all cancers. These are the hazard ratios by month since vaccine. So what we see is that the biggest difference in risk is in the first 1 to 3 months after the vaccine. Well, working in cancer for 20 years, I know that there is no way for cancer to be caused by something and appear in 1 to 3 months. Even the nuclear fallout from Hiroshima and Nagasaki took 3 years to give cancer. Smoking, asbestos, the most carcinogenic substances known to man take years, especially for solid tumors to form. So that's that's really unusual. The other thing is the signals didn't reproduce across doses. I mentioned about the booster, and I mentioned that the specific cancers that appeared higher didn't match. And so if this were true, if the vaccine effect were causal, that would mean that these vaccines were incredibly carcinogenic, way more than almost anything else we've studied, for it to increase detectable cancer 1 to 3 months after vaccination. But if it's that strong, why would it cause that effect after dose 2? But then after dose 3, there is no effect for the exact same biological substance. So that really suggests there's some bias. So is it possible that it comes from screening bias? Interestingly, these are the cancers that have routine screening in Korea: gastric, colorectal, liver, lung, breast, prostate, and thyroid is also commonly screened. And if we look again, what are the cancer types that showed the increase? Gastric is one, that's not on the list, but the others, thyroid, colorectal, liver, lung, prostate, breast. These are the ones that are screened. There's also evidence in the literature from various places that unvaccinated are more likely to skip cancer screening. There's a Japanese study that showed that the unvaccinated people were 27 to 53% less likely to do their scheduled cancer screening. And in a Canadian study, they found 40 to 65% less. Now, the authors even acknowledge in their paper that 1-year follow-up is probably not long enough to evaluate cancer risk. And they also acknowledge the possibility of reverse causation, and surveillance bias couldn't be excluded. So this study is valuable data, and the study is relatively well done, but you have to have extreme caution in interpreting these results. So if future validation is needed before you can really conclude that these effects are real biology, and ideally, it should adjust for the potential screening bias effect in this study, which is an example of ascertainment bias, where ascertainment bias is when one group is less likely to have their condition diagnosed, often because of differential screening, differential healthcare utilization, differential ages in the study, or differential follow-up. And I really want to point out this ascertainment bias because for chronic diseases that are now being discussed and really promoted by RFK and others, ascertainment bias is a major concern because any conditions that are not automatically noticed and diagnosed and recorded, but require screening or a lot of doctor visits or proactive response is subject to ascertainment bias. And that could color a lot of the studies that we see coming out. And it does affect some of the studies we see coming out. Okay, so in conclusion, thinking about these case studies, interpreting observational data is challenging, even for very educated and very smart people. And the changing dynamics of the pandemic and the post-pandemic period raise public interest in medical studies, and the socio-political dynamics feed social media misinformation and polarization. Okay, and so these factors can induce various types of biases that lead to well-known fallacies. So I mentioned a few key ones, and these are good ones to look out for if you're watching the emerging literature and seeing what's said and wanting to critically evaluate it. Base rate fallacy, various types of confounding, and I mentioned ascertainment bias. Simpson's paradox is sometimes a consequence of confounding. The post hoc ergo propter hoc argument that just because something followed something, it had to be caused by it. And also time frame bias, like we saw in the case control studies. So these can confuse the public, and they can be used by people with agendas to push narratives. So these affect the public discourse and social media, but they also affect scientific literature and policy. So it's critical for more epidemiologists and biostatisticians to be involved in scientific communications to make sure that they communicate a sound scientific evaluation of the emerging results that account for these challenges and draw valid conclusions. Okay, so now I'm going to shift a little bit and I want to talk a little bit about my experience. Why did I get involved in all this and what was my message? Well, I mentioned this was my goal. I put this on my blog page. I want to use my perspective to critically evaluate the emerging information, filter out biases, aggregate information, uncover insights, communicate in an accessible, balanced way, conveying uncertainty. My initial focus was on characterizing the virus, risk, spread, mitigation, and treatment strategies. And early on, the policies were formulated with incomplete knowledge and sometimes were slow to update. Many of my messages affirmed the public health recommendations that the virus was potentially risky, spread rapidly, and that it was important to take steps to mitigate the spread and protect the vulnerable. But other aspects of my message were more contrarian and went against what the public health recommendations or the media were saying. I argued that lockdowns were not feasible long-term and that targeted mitigation should be sufficient while reducing the collateral damage of the mitigation based on the emerging evidence of how targeted mitigation could work. Also, differential risk, that COVID wasn't equally risky to everybody, but it was differential by age and comorbidity status, and this should be taken into account in the messaging. Also, it was clear from this emerging evidence that the virus had aerosol spread, not just droplets, which was sort of denied by the public health leaders, which had implications for mitigation strategies, and also acknowledging that the data clearly showed there was immune protection after infection, which was something that a lot of people argued against to try and counter the Great Barrington Declaration that came out. But the data supported that there was. So these messages were well received on both sides of the political spectrum. But then when vaccines emerged as a game changer, this changed a lot of the narratives and kind of dominated the narrative starting in 2021, where the rapid development and dissemination of vaccines was a game changer. So it promised to get the virus under control and end the pandemic. And the clinical trial data and the initial observational studies initially demonstrated remarkable effectiveness. So to urge more people to get vaccinated, media and policymakers sometimes oversold the vaccines and made promises, overpromised what it could do, that later were disappointed when the data came out. And they also downplayed potential risks and induced strict mandates that were introduced as well to try and get more vaccinated for the good of the public health, but with political consequences. So then later data revealed waning effectiveness of the vaccine and the emergence of some genuine risks, myocarditis for mRNA vaccines and some clotting syndromes for the viral vector DNA vaccines. And so overall, as I followed through with this data, my critical evaluation suggested that the initial vaccination provided great benefits, as I described in the potential counterfactual scenario with Hong Kong, but not as great as initially advertised, and also that it was generally safe, but maybe not as safe as initially advertised, that there were real risks. So some of my messaging was negative towards the vaccine, pointing out the overselling of the vaccines and the lack of transparency in communicating the limitations and risks, perhaps with fear of dissuading people from getting the vaccine. Acknowledging the limitations and the risks that were evident in the emerging data, I questioned the need for universal annual boosters, and I pointed out that there were various improvements needed in the vaccine safety monitoring system. But overall, most of my messaging was positive, trying to counteract the misinformation that, as I'll mention, really started to go crazy at this time. That there were many claims that were demonstrably false or completely unsubstantiated by the evidence provided. So this made the vaccine skeptics see me as a pharma shill and start to attack me. Okay, and so coming out of the pandemic, I think that these situations in the pandemic sort of accounted for a rising anti-vaccine sentiment in the population. And some of the controversies of the pandemic have stoked this anti-vaccine sentiment. people angry about the strict mitigation and mandates that were imposed upon them, people seeing public health leaders as more interested in marketing the vaccines, especially when some of them may have financially benefited, and rather than transparently communicating the emerging knowledge, including the limitations and risks. And people heard stories of harm after vaccination that were attributed to the vaccine from either people they know or many stories on social media. So, so during this time, individuals built a strong social media presence, questioning vaccines and making dramatic claims of harms in terms of vaccines causing massive deaths, cancers, pregnancy loss, sudden cardiac deaths. And longstanding anti-vaccine organizations were energized and activated and grew in visibility, funding, and organization and support. And then the censoring of contrarian voices on social media further galvanized this community to come together, work together, share stories, narratives, and arguments, and gathering increased numbers of followers. So when the pandemic ended, this distrust of public health and in particular vaccines did not end. And now it's been further amplified by RFK's perspectives and history, and by his firing and replacing many public health leaders and advisory committee members with choices for the new administration. And the same polarized dynamic and the same aggressive promotion of anti-vaccine claims is occurring. So I tried to keep up with the claims, and I still do, and I engage with those making the claims to try and critically evaluate their evidence and communicate what I see back to them, to the public, and to the media. So, so this made me become very active in the media, that when claims or highly discussed papers emerge, I'll put it on social media, and because of the contacts I have, many of them will contact with me, get in contact with me to comment and provide information. And that includes fact checkers. So I'll help them with their scientific evaluation of claims. And I noticed that statistical and epidemiological fallacies are central to much of the misinterpretation and the misrepresentation. So one thing I see in this process is there's been a lot of hazards and disappointments. I've experienced threats, insults, accusations, and personal attacks. I see that people, and it comes from people that when you point out misinformation, they take it like you are gaslighting them and denying their experiences or what they know to be true. And then they associate you with a symbol of all they hate in government, public health, and political parties. And that can make you an enemy of some of the powerful, aggressive individuals and groups. And they look for opportunities to discredit you and silence your voice. So the question is, why do I engage so much then with this? Well, I want to correct misinformation and try and limit its propagation to the public. But not just that, I want to check if they're right. When I hear people make these claims, if they're true, I want us to discover them and make sure we validate them and take them into account. That's why I evaluate them. That's why I look at them so closely. And that's why I engage with these people. I think it's important to pay attention to contrarian voices, since they might see something others aren't, so that we can get clues also on how we can improve our current systems. So I mentioned I'm partnering with Annenberg, and I've written a draft of a white paper that summarizes the multi-layer vaccine safety monitoring system in the USA, describing how it's supposed to work, how you can properly or improperly analyze the data from the different components, but also pointing out ways the system needs improvement. So I mentioned ways that clinical trials need to be improved, ways that the passive reporting system needs to be improved in the data collection and in the rigor of the analysis, and to account for some of the biases in those data, but do a better job of uncovering the real risks that are out there. And then in the active reporting systems, which are medical records, utilizing more of the innovative and cutting edge observational data design and analysis tools, again, to better get true information from these, and to use multiple analytical approaches to assess the robustness and the reproducibility of these results, and to validate these results across multiple data sets, because we have multiple data sets within the US government, but also countries with centralized medical systems and international networks. And we should really have a coordinated, rigorous effort that is transparently described to the public, showing them that we are looking into all of the potential vaccine risks and showing if we think there's no risk that the evidence is presented. So I want to finish just by saying a couple things about how I do this. I think it's very important if you're going to engage in this way to do it with in certain ways and follow certain values. And to me, some of the key values you need to keep through this process is, first of all, respect and curiosity. And that's kind of, to me, a philosophy of life of how you should treat everybody. Respect everyone and try to be curious about why they believe what they believe. Try and understand their perspective, not just to debunk it, but to understand it. And don't argue with people's personal experience if they had a personal bad experience, but show sympathy for them and focus on the substance and not on ad hominem attacks, and be sensitive to genuine concerns and potentially true claims. And so, so my recommendations, if anyone else wants to get involved in this type of thing, is to again, try and be aware of circulating narratives and influential papers and claims. Don't just consider the peer-reviewed papers, but also the preprints and analyses that get circulated. Try and explain your conclusions in accessible ways. Focus on the substance, not ad hominem attacks, and avoid partisan statements. Ideally, if you're going to engage in this type of work and engagement and scientific communication, you don't want people to know your political views. Otherwise, half the country might just tune you out. You want to maintain credibility in the whole population. And you should always self-scout to make sure you're not falling for the same logical ideologies. So when you engage, many times you won't convince the person pushing the claims, but the reasoned evidence, if it's portrayed in a substantive and respectful way, might be able to convince some of the many, many followers of these people, and to help people who are on the fence discern which messages are valid and which are not. So I think I'll stop there.
Great. Thanks so much for an amazing talk, Jeff. A lot a lot there. I'm looking forward to going back through the recording and parsing a bit of this out. So a couple of questions, lots of good questions from the audience. I'm going to start with one of my own, which is one of the things that people who are critical of this kind of debunking will ask is, well, if this isn't true, if this isn't the cause, then what is? How do you respond to those kinds of questions? Jeff, you're on mute.
Oh, sorry about that. Yes. So how do I respond? It's tricky because sometimes it's like an entrapped question, but it reveals a fallacy of thinking where there could be many, many causes of things, like, for example, autism. And when people look at, oh, vaccination, number of vaccines have gone up, autism has gone up. Again, this is one of the fallacies, right? You know, that because they're occurring together that they're causing it, but there's so many things that change. So what I try to emphasize is that there's many, many factors. But what I also try to communicate is that we should look at whether vaccines contribute to autism. And I try to point out the many studies that have already looked at that link and are continuing to do so. And I encourage those efforts. But the key thing is it shouldn't be an effort where you start with the conclusion that it's vaccines and design a study to try and make the evidence. But what you do is you openly go into this question and you address it with a multifocal approach. I'm glad to see that this Autism Data Science Initiative that NIH Director Bhattacharya initiated funded a bunch of outstanding scientific groups that are really looking into the question in a varied way. It's not a biased assessment. And I think that's the type of thing that we need to encourage, but we need to acknowledge the uncertainty.
Thanks. So a question from the audience. What do you think is needed to protect against misleading scientific articles or to encourage responses from the larger scientific community to provide a critique?
Um, so I mean, I think we need, you know, peer review is imperfect. So sometimes papers get through that have serious flaws. So I think it's important to critically analyze those and describe those flaws, and again, to do it in an objective way. Um, and so, yeah, so I think that that's important. And that's some of the things that I'm personally trying to do. But I think that scientific community needs to do a better job, and the media needs to do a better job of it. And I think part of the problem is, especially with observational data, these issues can be extremely subtle and extremely difficult. And it's hard for people to recognize them, and it's hard to communicate them.
So another question from the audience. What public and policymaker reactions have you received when you've provided these explanations? And you've talked a bit about sort of the public reaction. How about policymakers?
I have not been in a position where I have direct contact with policymakers, so I haven't gotten to experience that.
Okay. A question about the Singapore data. Wouldn't the vax-unvax comparison in Singapore be the closest approximation to the question of what would the Omicron Delta surge look like sans vaccine?
The tricky thing is, especially in a place like Singapore, where the unvaccinated was such a small part of the population, it's very difficult to draw causal inference by comparing the vaccinated to unvaccinated themselves, because there's such fundamental differences. And there is a big difference, but that's where that's part of why vaccine effectiveness studies and other observational studies are very difficult to do, because there could be all kinds of confounding factors, and you have to adjust for them. Then there's always could be some that you don't adjust for. So you always have to be very cautious in interpreting that. But I think there was, there was a strong difference. And when you look at the data from all over the world in many studies and many designs, the fact that there was vaccine effectiveness to me is very, very clear. And it was very strong initially and went down in magnitude over time. But I think it's still not a great estimate of the counterfactual. We honestly never get to see that counterfactual. And I think that's one of the challenges, where people are looking back, and now that the vaccines are not as effective anymore, and they're not as necessary as they were in 2021, people forget how different it was when no one had been exposed to this antigen yet, and how much worse the outcomes are, and how much faster it spreads because there was no population immunity. And I think the inability to think through the counterfactual is the problem. It's very hard.
Thank you. There are 30 some more questions in the chat to answer. Sadly, we are out of time. I'm going to turn it over to Tori to wrap us up.
Thank you so much to both Dr. Hallman and Dr. Morris for taking us through that conversation. And thanks to all of you for joining us today. A recording of today's session will be available for AAAS members on the AAAS member community. Before you leave today, please take a moment to complete our short survey. The link is going to pop up as the webinar ends, and we're also going to be sharing it in the chat. Visit AAAS.org/community to connect with your section. And remember that you can join up to 3 sections by emailing myprofile@AAAS.org. Keep an eye out for more events that are going to be hosted by the AAAS sessions, and check out www.SciLine.org for resources and events to boost your skills for communicating with the media. We hope you took something great and valuable away from today, and have a wonderful rest of your day.
You.